So, once again, thank you for coming. And in this talk, I want to discuss the complex geometry of eigenfunctions. So, no, I'm afraid of it. Japanese chalk? I don't know. All right, so everything today will take place in the real analytic setting. So that means that we'll assume that the Riemannian manifold is real analytic and the metric is real analytic. So once again we're interested in the eigenvalue problem. So I use this notation for the eigenvalues. We're going to assume that M is compact, although it's really not important for anything in the talk. So let's see, we're going to assume this. We always assume that the eigenfunction is L2 normalized. And I will use this notation for the nodal set. Now, let me remind you of the Donnelly-Pfefferman theorem. So, in general, except in the case of surfaces, one has only very crude bounds on the hypersurface volume of a nodal set. And that indicates that it's going to be very hard to study nodal sets for general real C infinity metrics. However, the Hausdorff dimension of the nodal set, a Hausdorff measure, the surface measure of the nodal set in the case of real analytic case has very sharp estimates. So this is for the real analytic case. This was originally Yau's conjecture for smooth metrics. It's been proved for the real analytic one. And in their paper of around 1987, they proved this. The upper bound and the lower bound have rather different characters to them. But they proved it by complexifying the manifold and studying the complex nodal sets. As a matter of fact, I can give a very short proof of, I'm not going to do it today, but I can give a very short proof of the upper bound using the techniques that I'm going to discuss today. In fact, I used them recently to also prove the same theorem for what are called Steklov eigenfunctions, where if you use the non-global techniques, Fenghua Lin and Belova just studied the nodal sets for the Steklov case and got like lambda to the 6. So these techniques work for much more general equations than just the Laplacian and give very sharp results. But in any case, this indicates, the real analytic case is easier, and it's easier because we can complexify. So it turns out it's also easier for the problems I'm interested in, where we don't want to just measure the volume, but we also want to understand how the nodal set is distributed. And perhaps, people in the audience will think of other problems that would be equally interesting to study. Yes?
Can you recall how this type of estimate relates to the original goal of understanding the semi-classical limit?
Well, what the thing I'm going to do is going to achieve that goal. I wouldn't say that was even in their minds when they did this. So let me postpone that, because what I'm going to be proving will be doing what you just asked. Okay.
A ball of radius 10 lambda.
A ball of radius 10 lambda or 10 over lambda? Yeah.
Is there a local estimate for that size?
In fact, not for everyone. So the upper bound is pretty much holds everywhere. The lower bound, exactly the kind of thing they prove, is that they divide balls into good small balls and bad small balls, and they prove that roughly half of the balls are good. And in the good small balls, you have this kind of estimate. Okay? So I want to discuss let's say call it just Grauer tubes. So I think that some people will find the Grauer tubes to be of an independent interest. So what I'm going to do is going to be to go into the complex. So first of all, any real analytic Riemannian manifold has a complexification. So this is a complex manifold, and this is a totally real embedding. So this is a theorem. This is a theorem of Bruja and Whitney. It's not really that hard to guess why it's true. Locally, the manifold looks like Rn, and when we complexify it, we get Cn. So we can complexify, holomorphically extend charts, and try to glue things together. So as an example, let's just take a flat torus, because I'm going to use this example later on. If we complexify a flat torus, we're just going to get, going to get like, Cn modulo Zn. Yes, it is. It is. Let me think for a moment. And then of course, if you complexify a sphere, you just get the equation over the complex numbers. It's a real algebraic variety. So we can just interpret it over the complex numbers. So those are some examples. Now, the key object we're interested in is called the Grauer tube function. It has a kind of unusual history. So it was not immediately observed, but this is what it is. We look at the distance function squared between points. Let's say near the diagonal of m cross m. Okay? And that's, of course, this is a real analytic function near the diagonal. So we can holomorphically extend the distance function to a neighborhood of the diagonal in the complexification. So we can then define rho of z, where z is in the complexification of m. We can define rho of z to be minus the square from z to z bar. So why do you do that? Well, let's take a flat torus, or Euclidean space, it doesn't matter. So then the distance squared is just x minus y squared. So if we put in x as z, and let's say y, we're going to put in y as z bar. And let's write, this is a very useful notation, let's write z as x plus ix. Then this is just going to be 2ix squared. So it's going to come out to be negative. So we put a minus sign in front of it to make it fun.
But just to make invariant sense, you want to give one of those copies of MC the conjugate complex?
Yes. Well, for what we're doing, but we're not going to be thinking that way.
No, they don't want to.
Well, let me put it this way.
MC has a complex conjugation already.
All right. Well, let me put it this way. When you have a complex manifold, I think you're thinking the following thing. If you have a complex manifold, then the complexification of it as a real manifold is m cross m bar, naturally. I think that's what you're thinking. But here I'm taking an underlying real manifold. I'm not making a complex manifold, so it doesn't really make any particular sense to do that.
I guess the key point you want to make is that you can set it up so that MC comes equipped with an anti-holomorphic involution. And that's
yes.
Yeah.
We have an anti-holomorphic involution here, z goes to z bar, whose fixed point set is the underlying real manifold. So what's called the Grauer tube function. So the tube function is called the square root of rho. Or actually, it might make more sense to divide this by 4, just so we get the nice answer for a flat torus. And then this is the Grauer tube function. So this looks just like absolute C for, like, let's say Rn. Okay? Now, this function here satisfies the following equation. And this is actually how it was originally discovered. So, fact is that it satisfies a homogeneous Moser-Ampère equation. So, let's let M be the dimension of M. And it satisfies this homogeneous Moser-Ampère equation. So, here by
Symbol.
big symbol, big symbol. When we take the delta function on R and you integrate a function, it means I'm integrating over the real manifold with respect to the metric volume form.
It's not quite the homogeneous Moser-Ampère. It's a homogeneous Moser-Ampère most places.
Well, that's an interesting point. So if you look in the papers of Lempert, so this was due to Lempert and Serkey, Pittman, Wong as well, Gilliman and Stenzel. And in fact, they started from the opposite point of view. They wanted to find solutions of the homogeneous Moser-Ampère equation in this setting. And they proved that first that if you really wanted the right-hand side to be 0, you only get constant solutions. So you needed to have what they call minimal singularities, square root singularities along some real core. And so this is the equation. Now, oddly enough, all of them wrote their papers without ever pointing out that this is the formula for the solution, and that if you use this formula, you can just directly prove it. They argued very abstractly. So it wasn't, if I remember right, it really wasn't understood that way. Another strange expository point is that, to my knowledge, nobody ever puts the right-hand side in correctly. Maybe somebody has seen somebody do it. They usually just write 0. Usually what you say is it's 0 on MC minus MR. That's the statement you normally see, which is kind of ambiguous to me. But anyway, okay, so that's the Grauer tube function, which means it's an extremal. It's a plurisubharmonic function. It's a plurisubharmonic function, and the solutions of the homogeneous Moser-Ampère equation are extremal functions, like harmonic functions. They're generalization of harmonic functions, but we're going to insist that the competing functions have these same singularities. Otherwise, you get the constant function. So
actually, to get a current in the right dimension, I guess it's supposed to be the current of integration for the metric volume form. You start off with a metric.
So let me think if I understand.
It's not literally the delta function, because if it's supported on something of real dimension.
Well, delta sub
N.
P, yes.
So
integration.
You're integrating against a particular densities, presumably the metric densities would be the statement, because you have a metric that determines your.
Yes.
Yes.
And is there a constant is there a constant in front of the delta, or is it?
Well, 2 pi or something, but who cares?
Well, it often makes a difference.
No, there's no interesting constant. So,
So you're working with the convention that 1 equals 2 pi equals I.
yeah, for sure. Now, in fact, somebody told me this ought to be minus I, but I'm not going to check it. Now, in any case, rho is strictly plurisubharmonic. So I guess everybody is very familiar with this notation. So rho itself is plurisubharmonic. And in fact, we're going to define omega rho to be I dd bar of rho with the correct sign to make this positive. Either I or 1 over I. Eric, you know right away. Is it I or 1 over I? Okay, Alex. Maybe a 2 pi too. All right. So this is the Kähler form. And if you take mg and you embed it into mc with this Kähler form, this is, or more precisely with the associated metric, this is isometric. In other words, if you restrict this form to the tangent space to M, you get the original metric. And that's the way Gilliman was originally thinking of it. He wanted to solve some kind of Cauchy problem for the homogeneous Monge-Ampère equation, and he wanted the initial data along this, along the real points. You know, the real points as half the dimension, right? So it's a very singular Cauchy problem. This is 1/2 the dimension of M sub c. It's a totally real submanifold. But anyway, that's the way they thought about it, and somehow it took a long time before they realized. Perhaps it was in Gilliman and Stenzel. So this is weakly Polari subharmonic. I mean, the I dd bar of square root of rho is greater than or equal to 0, but it has a one-dimensional null foliation. You know, the kernel of this. So the kernel of dd bar square root of rho is a complex. It's one complex dimension. It's the null space. You know, this thing, the determinant of this mixed Hessian is 0, so it has a kernel. The kernel automatically is a complex subspace at every point, and in this case, it's the leaves of it. It's integrable, and the leaves are one-dimensional. And they basically, what they are, so this is called the Riemannian foliation, or Riemannian or Monge-Ampère foliation. And essentially, the leaves, the curves, are geodesics. So let me explain what that means. But they have a natural interpretation in terms of the Riemannian geometry. So let me explain what that means. And put the, it's in MC. Null foliation. So I'm looking at dd bar of square root of rho. It's a 1-1 form on MC. Okay. And so it has, at every point, there's a kernel, and it's integrable. It's one-dimensional. One complex dimensional. And so actually, it's very nice to explain what it is. So you might call this a canonical identification, which kind of explains its significance in quantum mechanics, you might say. So in other words, let's look at the cotangent bundle of M. So there's a natural map from the cotangent bundle of M into the complexification. And in fact, we're going to have to fix, really I'm going to look at a ball of some radius epsilon in the cotangent bundle, as we'll see in one moment. And I'll call this map E. And the map goes as follows. This sort of explains everything about the geometry.
Around M of radius epsilon, or when you say a ball, you meant?
Where are we looking? Here?
Yeah. Is that a
ball bundle.
Ball bundle. So it's a two to the neighborhood.
Ball bundle. So, no. I mean, at every point x, you have the tangent. You have the cotangent space at the point, and then we take a ball of radius epsilon in the cotangent space at every point. So it's a ball bundle. So I denote a covector by x and c. So this we have a point x in a direction c, and then this is defined by x at x I times c. It's really, this is the whole story when you want to study the Grauer tubes. So what's going on is that we have our manifold, our real manifold. We have a point x, we have a covector c. We then rotate it into the complex direction, and we go along the geodesic flow in imaginary time. So for example, if M was hyperbolic plane, for example, then this would be a great circle. Okay? So we, of course, if we went along the exponential map in this direction, we'd stay on the manifold. It would just be a geodesic. But we're going off the manifold into the complexification when we analytically continue. So this is the analytic, I'll write AC for analytic continuation. analytic continuation of the exponential map x of tc to imaginary time. So this map is very significant because the cotangent bundle, of course, it has a natural symplectic structure on it. And if we pull if we go by E inverse and we pull back the symplectic form, then we get the Grauer tube form. Everything that we actually do on the Grauer tube setting is going to be mirrored by something that takes place in the cotangent bundle that you're probably familiar with. So, you know, actually Lempert and Sarke thought about themselves as just putting a complex structure on the cotangent bundle adapted to a Riemannian metric. On the other hand, for what I'm doing, it's more natural to think about things in the complexification of the manifold than it is to think about them in the cotangent bundle. But the moral of the story, the moral is that the complexification equals phase space. Classical mechanics takes place in phase space. Then we quantize it and make it take place in some Hilbert space. But this complexification of M is just a model of phase space. So it sort of explains why things are coming out so nicely. So what are the other sort of dictionary of identifications? Well, what about the null foliation? Let me explain what I meant by geodesics. So, well, first of all, rho under E, so under E, you know, rho corresponds to the length squared associated to the metric. Square root of rho, the tube function just corresponds to this. So we usually use the notation m epsilon is the point zeta where this is less than or equal to epsilon, and this corresponds to the ball bundle of norm epsilon. So these are diffeomorphisms. However, what else? Well, in Riemannian geometry, you have a Hamiltonian vector field. You have the Hamiltonian vector field of any Hamiltonian. So in particular, we can take the Hamiltonian vector field of either of these Hamiltonians. For certain reasons, I prefer using the homogeneous version. And then the integral curves of this Hamiltonian vector field, these are what we call geodesics. So we think of geodesics, a geodesic is a Hamiltonian orbit. So we think about lifting the geodesic to a sphere bundle by putting the unit tangent vector at every point. Or we can lift it to the bundle of radius epsilon by making the tangent vectors of length epsilon. So, in that sense, here, if we look at the flow, if we look at the Hamiltonian vector field of square root of rho with respect to the Kähler form, these correspond to geodesics. So geodesics, the phase space geodesics or cotangent space geodesics, they are naturally arising in the tube context as Hamiltonian flow orbits corresponding to the Kähler form on the cotangent bundle.
Is the reason why that two-plane field is integrable? Yeah.
It's complex, holomorphic. I mean, it's complex. So.
Well, the
mean,
point is that you're actually looking at a leaf that passes through the real slice. So there's a fully...
No, actually, no.
Well, if you by a real geodesic...
Well, you see, all these things become singular along the real slice. If I had used c squared here, the geodesic would just, have length 0. It would just be, Oh, you just reminded me. So...
What I'm trying to say is that there are geodesics off of there are complex geodesics off the real slice, right?
Yeah. So I mean, here we are. Here's MC. So I didn't say yet what the Riemannian leaves are. So a leaf here is R plus times gamma dot of 0, gamma dot of t at every point. So, when you take the geodesic, you could look at the tangent vector of any length. So I just multiply it by all positive lengths, and I get a half plane. So this is actually what the leaf is. So if I map it over under this E map, I'm going to get, so here might be m sub r or something like that, and then I get a leaf. I get a leaf over here. So this leaf, the leaf over here, if you take a leaf, I'll call it L, and you intersect it with the boundary of a Grauer tube, then this is just a real curve. This is actually going to just be the Hamiltonian flow line. So
it's just scaling.
Scaling. Yep. Scaling makes sense, on the cotangent side. Let's see. Maybe I mention a problem that's not known. So, this map E usually does not extend, does not always extend as a diffeo to the full cotangent bundle. There exists a maximal radius. And, you can see why, because you're going in if it's like on a hyperbolic plane, you start going in this direction and it's a great circle. So at some point you're going to hit cut points, and this thing will cease to be a diffeomorphism. So a problem which has not been studied very much is calculate it. Calculate what is the tube radius where E is a diffeomorphism. It's unknown in general. As an example, it equals pi over 2 for hyperbolic space. So that's a nice calculation, not completely trivial even for hyperbolic space. For the sphere, for Sn, the tube radius is infinity. Everything works out because, the geodesics, when you do the imaginary geodesics, they're like hyperbolic ones, and you never have cut points or conjugate points. So it just goes on forever. All right, now, let me see. Okay, so now quantum mechanics. So maybe I mention that in the very early days of quantum mechanics, Schrödinger, this is Schrödinger, but let's say sort of more like von Neumann, Hermann Weyl. They showed that, I don't want to explain this too much, but they showed that there's exactly one irreducible representation of the Heisenberg group. I don't even want to define it, but it is implicitly going on in this problem, but I don't have enough time to go into it, in Rn. So this is called Stone-von Neumann theorem. With a given central character, I'll just say with a fixed Planck's constant. Some years later, independently, I guess, Valentin Bargmann and Vladimir Fock found that there is a different model for this representation on L2 of Cn and functions which are square integrable with respect to this weight, this Gaussian weight. And there's a natural transform between these called the Bargmann transform. Now, things in quantum mechanics are invariant under unitary equivalence. So you can either use this model or this model, and they're equally valid models for quantum mechanics. This is often called Bargmann-Fock space, or some people just call it Fock space. So, okay, so you have this Bargmann-Fock space. Now, we'll see that in the Riemannian context, L2 of Rn just corresponds to the real domain, and this one just corresponds to the complexification. So when we go into the complex and we do quantum mechanics in the complex, we're just really doing Bargmann-Fock in the setting of Riemannian manifolds. It's a perfectly natural thing to do. We're just generalizing Bargmann-Fock, if you like, from Rn to a general real analytic Riemannian manifold. You can carry that quite far because all of Paley-Wiener theory is basically about, the holomorphic extension of the Fourier transform, Bargmann transform. And so in a sense, we're just understanding Paley-Wiener theory on a Riemannian manifold instead of Rn. So
what's the operator over there?
Operator Wien row.
Laplacian was up there, right?
Oh, yeah. So these are called Toeplitz operators. When you go by the Bargmann transform, it just converts Schrodinger operators into what are called Toeplitz operators. Okay, so now the key for us, the key for Riemannian manifolds is that there's a very simple Bargmann transform. The French like to call it the FBI transform. So, in other words, we take u of t, which is e to the I t square root the Laplacian. So this is called the wave group. So, or half wave group, if you want to be like that. So this is cosine t square root of Laplacian plus I sine t square root of Laplacian, and these are all defined by the spectral theorem. We can, make sense to take functions of operators. So this is a unitary operator. And in general, when we talk about hyperbolic methods in studying eigenfunctions, it means, so if we start off with this as minus lambda squared of phi, then it says the following, that this on phi is e to the I t lambda on phi. Phi is an eigenfunction of this wave group. Now, this is the hallmark of the global method. People who do eigenfunction analysis or harmonic analysis really locally on a small ball, they study this equation, but they don't even assume that this function phi is a global eigenfunction. It might just satisfy this equation on some ball. Doesn't satisfy it globally. However, to make this equation true, the function phi must be a global eigenfunction on the Riemannian manifold, and then this makes sense. So this is the input for global techniques, and you need something.
A local operator.
That is true. It's a pseudo-differential operator of order 1. So, but anyway, by the way, you see, historically, this operator is a lot easier because it's really just a function of the square root of Laplacian. So Hadamard studied this operator, wrote down a very beautiful parametrics. This one's much more complicated because it's not a function of the square root. Now, if we just write it out in terms of eigenfunctions, this operator looks like e to the I t lambda j, phi j of x, phi j of y. These are real, so I won't put a bar on it. So this is our propagator. The game I'm going to be playing, you could play for Schrodinger operators or in a much more general context, and it hasn't actually been done. So what I'm going to do is I'm going to look at this operator at imaginary time. So this I'm going to call the Poisson operator. I take u at imaginary time. Let's call this a z and a y. So what happens, I sum, and this is going to be e to the minus tau lambda j. It's going to be the analytic continuation in the z variable, and then this one stays the same. So this is maybe I'll put a c here. So this is really a theorem. So this is a theorem. In fact, there's quite a lot of parts of this theorem. So this was a theorem that was originally stated by Boutet de Monvel in something like, where was it? Maybe 1986. He stated that the wave kernel had an analytic continuation of this kind, and as a complex FI Fourier integral operator. I will come back to this later, but I don't want to define it now. It's as a complex Fourier integral operator, which was something which was earlier discussed a lot by Sjöstrand in particular, Mellin, and other people. So this was But he really never proved it. He just sort of stated it. And myself, around 2011, gave a proof of this. And then Gilles Lebeau, who was a student of Boutet-de-Monvel, gave a proof of this maybe 2012. And then Matt Stenzel. So the proof of Lebeau and myself are almost sort of very similar. And I mean, I don't, what I really view is that this is really due to Hadamard. Somehow, you know, in the history of the subject, it was ignored that Hadamard himself in 1920 had actually studied the analytic continuation of the wave kernel. And in fact, I really just updated Hadamard's work and explained some things about it, but I would say this theorem is really due to Hadamard. Okay, so it's not just that it has an analytic continuation. It's really more that the analytic continuation has a very special structure, but I don't want to explain what it is. So now, however, keep in mind that the wave kernel and the wave kernel is a very special kernel. This is also what's called a Fourier integral operator. Z in the, so, thank you. So this is where the square root of z is less than or equal to tau. Otherwise it won't. So let's just do an example. This was all that Boutet-de-Monvel actually wrote down. He said, well, let's see what u of txy is on Euclidean space. It's just written as a Fourier integral of e to the I tc, e to the I c x minus y dc. He said, well, let's put in, let's change this one to minus tau. Here it's understood that tau is positive. It's a tube radius. And let's change x. Let's change x to z. Okay, and then ask when does the integral converge? And just by the Schwarz inequality, the integral converges. You know, this one over here is less than the modulus of z times c. You need the exponential decaying. This is exponentially decaying. You need the exponential decaying factor here to beat the exponential growth in this factor. And as long as, well, as long as this is true, e to the minus tau norm c, e to the c z in modulus, or you know, this thing is decaying. I'll just say it's decaying. And the integral converges in c. If you set them equal, you get a distribution. You get a distribution again. You get singularities again if you set them equal. And actually, that's what we're most interested in. We were actually most interested in setting this equal to the modulus of z. So that says that z is on the maybe I didn't define that notation, but the boundary over here is the set of points where the square root of rho equals tau. So that's like a sphere bundle.
Norm z, that square root of rho z is, in this case, norm z.
Yes.
That thing you square root of rho.
That's true, but what's more important is that this is the Grauer tube function.
Okay.
Yeah. So you can generalize this. That's what all that one does. You can generalize it. This has a continuous spectrum. You can generalize it to discrete spectrum and prove that this is exponential. This is rapidly converging. As long as this is less than tau, when it equals tau, you get a distribution kernel, and it's got very interesting singularities. So that's what you have to prove. All right, now we come to, so first of all, I can state now sort of the main problems and what the main results are, and also what some open problems are, because I think it's a fairly rich subject and there's not that much known about it. All right, so the first thing that we observe is that if we take this Poisson kernel and we apply it to an eigenfunction, what it does, first it multiplies like that, and the second thing it does is it analytically continues the eigenfunction. So this is a really great thing. Simple. And yet this Poisson kernel, which has so much structure, does the work of analytic continuation for you. And actually, as I will explain, no, I mean, it's just the analytic continuation of the fact that u at t phi j is e to the I t lambda j phi j. Just look at orthogonality. Plug in a phi into here. By orthogonality, it sifts out just the term with the same eigenvalue. And then you get that. Okay? So now the value of this theorem is that this kernel has a lot of structure. That's the whole tool in the subject. So I would say that in the work that I do, the key point is to exploit the structure of this kernel. It's a Fourier integral operator of complex phase, which I won't really have time to explain, but this is where the heart of the matter is. This is why the techniques I use are different from Donnelly Pfefferman or Fanghua Lin or whatever, because they never use this equation to study the analytic continuation of eigenfunctions, and you can just get a lot out of it. So, for example, you can get the growth. You can get the growth of phi j in the complex domain in MC out of this equation. For example, you can show that if you take u of I tau c phi j c at z, that this thing is going to be basically less than this thing is going to be less than e to the minus tau lambda j. This thing over that's right, lambda j to some to the power n, let's say. So I mean the point is that but on the other hand, this thing is just e to the minus tau lambda j, and if we cancel on both sides, if I didn't do this quite correctly, what I mean is, let's put it this way. No, I didn't say that quite correctly. From this thing, you can see that the norm of phi jc is less than or equal to, at z, is less than or equal to this times lambda j to the n. You can just read it off from that. So this thing only magnifies, one of the facts about a Fourier integral operator, it only magnifies the L2 norm of phi or ck norms of phi by lambda to some power. That's part of the structure of a Fourier integral operator kernel. Yet, it's the complexification times this. So the exponential factor here must cancel the exponential growth factor here in order to be consistent with what a Fourier integral operator does. So you can deduce facts of this nature, many facts of this nature. So this gives you the growth of phi j in the Grauer tubes very easily just out of the Fourier integral structure of this wave kernel. All right. Now I want to talk about nodal sets. You can get the growth of the holomorphically extended eigenfunction. So this is like basic Paley-Wiener. We can easily get the growth rate of the eigenfunction in the complex domain out of the eigenvalue formula, because the left-hand side is polynomial growth in lambda j. So the right-hand side is polynomial growth in lambda j. And that means that the phi j, that the e to the minus tau lambda j has to cancel out the exponential growth. And in fact, it's sharp because you can calculate the L2 norms on both sides. So that's exactly the exponential growth rate. All right, so now I want to come back to this problem here about looking at the complex nodal sets. So I want to, instead of looking in the real domain, I want to look in the complex domain and study the nodal sets of the holomorphically extended eigenfunctions. And the thing that's also easy in the complex domain is that as a current, we think of this as a current of integration. This is a current of integration, meaning that let's say that if you want to pair this, I'll think of it as a measure rather than a current of integration, because that's really what is going to come up here. And if I pair it with a test function, then this is by definition the integral over lambda phi lambda c, the phi, of f with respect to the Grauer tube Kähler form to the power m minus 1. So this is Werdinger's formula that the natural surface, Riemannian surface measure induced by the Riemannian metric omega rho, the natural surface measure is on a complex analytic hypersurface, it is just the Kähler form to the power n minus 1. So now we have a Poincare-Lelong formula that gives this as I dd bar log of phi lambda c. So we have an exact formula for the delta function on the little set. This is the formula people use just like every minute in complex analysis. You just really don't have an analog of this in the real domain. So this is one of the key reasons why we can do so much more in the complex domain than we can in the real domain. So this is a generalization of the fact that if you take the delta function of this, you get like 1 over 4 pi times delta function at 0. You have a higher dimensional generalization of that formula. So our goal, so let me state a problem and then a theorem. So well, an observation is, I'm a little bit running out of time, so I'm not going to prove everything. An observation is that if you look at this family, so let's look at this. So what is this family over here? This is a sequence of plurisubharmonic functions. And where this function is 0, this is minus infinity, but these are uniformly bounded above. By the argument I was basically just sketching. These are uniformly bounded above, basically by square root of rho of z. So basically. So this is a family that's uniformly bounded above, and one of the more foundational facts about actually subharmonic functions rather than pluri is that this is pre-compact. This is pre-compact in LP of the Grauer tube for p between 1 and infinity. There are actually stronger theorems than that. But it's actually a pre-compact. So you actually have strong limits, and that's another huge gain by working in the complex domain. It's pre-compact. So problem is, and this is a problem about any Riemannian manifold. It's a completely general problem. Find the limits. Find the limit points. Now, anybody who's been introduced to quantum chaos knows that you study the same question without taking a log and dividing by lambda. You L2 normalize, but you do that. So this is a completely different problem. And although in every example I've ever looked at, the limits are invariant under the geodesic flow, I do not know any theorem. I've tried many times, and I don't see how to prove that. So find the limit functions in other words. Well, I'd like to. So, let me explain that in a moment. But why are we interested in that? Because, and then I'll give you an example. And an example of this. So if you can, right, then if you take I dd bar of a sequence, 1 over lambda jk log phi lambda jk, So if we take IDD bar, suppose that this tends to some function u in the limit. Then, let's say LP norm. It's a theorem that if it even tends in the weak topology of measures to u, then it tends in every LP norm to u. So then this tends to, in the weak star sense, in the sense of measures or currents, this tends to I dd bar u. And what did we just find? This is equal to 1 over lambda jk times the current of integration over the nodal set. And we would have just found the limits of currents of integration over the nodal set. So let me state a few theorems. In general, it's very hard to find weak limits. There's not much to work with. But so maybe I'll state as theorem 1. So this really I proved in 2007. But the theorem is that if the geodesic flow is ergodic, then 1 over lambda jk log of the eigenfunctions tends to square root of rho. So this is what we call density 1, for almost all of the eigenvalues. You might have a sparse set of exceptions, which we never identified, in what's called the QUE setup. It's all of them. So we can actually figure out you might have density 0. So, but in any case, I mean, conjecturally there is no bad subset, but in any case, you actually can completely do this. So let me just give you an example, which is kind of trivial, but it's the only computable example to see what this is like. So I realize this looks trivial, but it'll explain to you what the theorem is saying. So let's say that M is the circle, and then the complexification is a cylinder, right? It looks like the cotangent of the circle. It looks like C mod Z. And the eigenfunctions here are, let's say, sine of k, sine of kx. We're not worrying about the normalization factors. So phi k of C is sine kz. Now, it's a good question, by the way, for a qualifying exam in a complex analysis. What are the complex zeros of this? Well, first of all, what are the real zeros? So let's just say that they're the kth roots of unity and not worry about the details. They're basically the kth roots of unity. So along the circle, you get kth roots of unity. What about the complex zeros? If you analytically continue the eigenfunction, what happens to the zeros? When was the last time you gave a qualifying exam? It's the same. All of the zeros are real. All of the zeros are real. And it's kind of interesting about that, to think about that for other eigenfunctions. That often happens for eigenfunctions in one dimension for Sturm-Liouville problems. So that's what it is. And as k goes to infinity, the current of integration, if we take the current of integration over, let's say, e to the 2 pi I m over k, let's say m goes from 0 to k minus 1, this just tends to the d theta along the circle, but really this is times the delta function in the vertical direction. So we get that answer. Now that's, if you first calculate this, which I did before starting to think about a generalization, you might think there just is no equidistribution theorem for nodal sets, because for Riemannian manifolds, this is like far from being equidistributed in phase space. However, what did we get by this? The Grauer-Tube function is just C, and so we're just asking, is this the same as IDD bar of the length of C? Maybe there are factors of pi and things thrown in. And this is just the Laplacian of C. And of course, it's d squared by dx squared, which doesn't touch the C. So this is just the second derivative. and you get the same answer. So that's actually the kind of theorem it is. And you notice it's very singular on the zero section. Very singular on the real zero set. That's really interesting. The complex zeros are not somehow equidistributed in phase space. They are highly concentrated on the real points, which very heuristically suggests that if you know the complex zeros, you might be able to deduce facts about the real zeros. But I have never found a principle in complex analysis which allows one to do this. So, I want to state another result, because given that the one-dimensional case is so singular, I thought, well, this would be very interesting to do a restricted version. So I mentioned yesterday that it really helps to, let's say, geodesics. It really helps in this subject. You get a lot of information by intersecting nodal sets in geodesics. So what does that mean? A geodesic is a map. There's an interesting dynamics question here, which I'm going to ask you after my talk. There's a geodesic, we'll think of it as a curve in M. So M might be this, and it might be a closed geodesic or maybe a long one, but at the moment, let's think it's closed. So we can complexify this. Here I'm looking just at the geodesic in M. I can complexify this and look at the holomorphic extension of this into a strip like this. So here's the real axis, and here is a tau. And I look at it as a strip, and it goes into the complexification of M. Okay? And then I have my eigenfunction lives here, so I'm just going to pull back the eigenfunction to the strip. And now how hard can that be? We now have one complex variable. So this is a function just of t plus I tau. Namely, I'm just looking at the complexified eigenfunction on the strip. Now, in one dimension, we got this very singular answer, and it turns out that that's exactly what happens. Almost the same thing happens in all dimensions. So in higher dimensions, we know that there are complex zeros which are not real, because the complex zero set's a hypersurface. It's obviously not going to be just real. But you get the following theorem. So this one, I guess, appeared maybe in 2013, maybe, or 12, or something like that. That if you look at the current of integration, so let's take the current of integration. How should I write this? The nodal set for the pullback. And this is really just going to be a sum over the points where this is 0. It's a discrete set of points. And then I just put a delta function at that point. So in other words, I have a strip here, and I pull back the eigenfunction to a strip, and so I get some complex zeros. Remember that yesterday I was discussing how you have to have an unbounded number of real zeros as lambda goes to infinity, at least like log lambda, but I don't know how many real zeros there are. So the theorem is that, again, if I divide by lambda here, let's say put in a lambda j everywhere, that as lambda tends to infinity, this tends to the delta function at tau equals 0 times arc length along the geodesic. So what these zeros look like as lambda goes to infinity is that they're really condensing along the real geodesic, and they're kind of uniformly distributed along it. So this answer looks very similar to the case of the circle, but in the circle we had only real zeros, and here we have real zeros together with almost real zeros. There are only a possible sparse set of outliers to that. So once again, once again, I guess I'm over. I just finished. My time is up. It's a interesting question whether anything in classical complex analysis tells you that if you have so much clustering of complex zeros around the real axis, and you complexified a real eigenfunction, I mean, it was a real function in the real domain, and then we complexified it, is there any way you can show there are at least some real zeros just from that information? So I'll stop here.
The right-hand side is sort of like classical mechanics, just the geodesic flow.
Well, this is, see...
But let me say, just say yes. So I can
classical mechanics is this, it's this theorem. It's the semi-classical limit.
Semi-classical limit.
Oh, lambda goes to infinity is a semi-classical limit.
No, but I mean, if I think of the classical limit as being the geodesic flow,
Right.
You're sort of saying these zeros.
So let me say one thing though, right?
Yeah.
So I can't say yes to that.
Okay.
You see, I just picked a geodesic and complexified it. The reason we got a geodesic out is we put a geodesic into the theorem. If I had taken any other curve and complexified it, I would have gotten something like this, but it would have turned out that I would get a cloud of zeros everywhere with some kind of, but I would get a cloud, a fuzzy cloud of zeros, which would not concentrate just on the real point. So that's the only place where the geodesic became a distinguished curve. So if that feels to you like a yes to your question, then I'm the...
This discussion of zeros corresponds to the quantum phenomenon you're studying.
So let me, because I didn't explain the proof. So the ergodicity, so let me just say a few words, that the ergodicity of the geodesic flow is used to prove the following fact, that if you take the modulus squares of take the complexifications and take their modulus squares, and then divide out by the L2 norms, let's say at the boundary of one Grauer tube squared. So this is L2 normalized, but I do it one boundary at a time. That this tends to the square root, this just tends to 1 in the weak sense. This is quantum ergodicity, but I've done it in the complex domain rather than the standard result in the real domain. So this is actually using ergodicity of the geodesic flow, and you prove that. And then that's the only use of classical dynamics. And then out of that, we have to study what looks like a very different limit problem. And the reason that these things turn out to be the same is that this says if we take the log, no, I don't mean to that. No. This one tends weakly to run. If we take 1 over lambda j log of this, it tends to 0. And we prove that actually forces numerator and denominator to have the same order of magnitude. And then all we have to do is calculate 1 over lambda log mod of the L2 norm. And that we can just do using the wave kernel, the Poisson kernel. So this tends to 1 over lambda of the ratio tends to 0. We really are interested in the numerator because dd bar of 1 over lambda log mod of the numerator is the current of integration. But it reduces us to proving the only thing we ever, in fact, actually have to calculate is the L2 norm of this on the boundary of the Grauer tube. And so it turns out that this tends to tau. And we use the Poisson kernel just to do this calculation. It's sort of like saying, I take the Poisson kernel in the real domain, Poisson kernel in the real domain, and then I swap this over to this side as an adjoint and calculate out what it is. So this is the place where dynamics is used. You get the ratio. Taking 1 over lambda log of it is completely not anything that you study in quantum mechanics up to this time. But that's ultimately what we need. So that's why this is, in general, this is a really new problem to try to figure out what are the limit points of the sequence. In the case of ergodic geodesic flow, we get a kind of perfect answer to the question. I've done it for completely integrable systems. You get something radically different. But anywhere between completely integrable and ergodic, I have no clue what the answer is. I have a lot of conjectures, but no clues.
Beyond integrativity, because some mixing, you probably can estimate the rates of convergence.
Well, that's a very interesting question. You know, if you have additional structure to the flow, like mixing, then in fact, somewhere in the 80s, I proved the quantum mixing theorem. What does mixing additionally bring to you? And unfortunately, mixing does not bring you more about the individual eigenfunctions. What mixing does is that it allows you to study linear combinations of eigenfunctions. So you get more general result, but it does not, in any theorem I've seen so far or thought of, it does not allow you to get a deeper information about the individual eigenfunctions. Mixing is about off-diagonal matrix elements. Off-diagonal. And we're looking at the squares. So mixing would tell you something about phi j times phi k when j is not equal to k, about the semi-classical limits of those quadratic things when they're not the same. That's what it tells you.
Lower bound from your theorem, why restrict to real MR of the nodal set to get an
Why do you say we don't get a lower bound? We get an asymptotic formula, perfect formula. Upper bound and lower bound, asymptotic.
the nodal set on R?
Oh, right. So that's I mean, I don't know. I mean, this is a sort of a question, you might say, of several complex variables or complex analysis. I've tried to think about it and look to find results about it. I don't know anything. Namely, you know, out of the knowledge of the complex zeros that they accumulate so much in the real domain, can you get a lower bound for the nodal set in the real domain? Well, first of all, don't forget this is the analytic case. So Donnelly and Pfefferman already proved it. So maybe you don't want to spend too much time on that problem, but nevertheless, we'd like to know about the distribution of the zeros in the real domain. But for all we know, there could be almost essentially, what if all the zeros were actually just 1 over lambda away from the real domain? Then in the limit, they pile up on the real domain, but there just weren't any real zeros. We know it doesn't happen, but you know, we don't know much about it.
About distribution in the complexification of geodesic, it is for typical geodesic, or
This actually requires a certain assumption on the geodesic, which is called asymmetry. Which you see, like, if, for example, I had a symmetry of my manifold like this. Suppose I had a symmetry and I chose the geodesic to look like that, and I have a left-right symmetry. Then suppose we take the odd eigenfunctions, they will completely vanish. So the theorem would not be stating the correct result there. They would simply vanish everywhere. So we actually need we need asymmetry. I assume that the geodesic is asymmetric. That means that you know, there's no left-right symmetry to it. That's it. It's a general theorem.
So it's, for example, just fine if it's a periodic geodesic.
Periodic geodesic is fine as long as it's not a symmetric one. Yes.
I guess, well, all your techniques need an analytic, right? In this method.
Need a what?
This analytic assumption, right?
Yes.
What about smooth?
Well, you know, that's another very interesting question because, you know, in the world of microlocal analysis, you know, you can use techniques of analytic microlocal analysis even for smooth metrics. And starting with like Hermander and Mather, Malgrange and people like that, people make almost analytic extensions rather than analytic extensions. So, you know, you might dream that if your metric was like a Gevrey metric, or, you know, if you can somehow do almost analytic extensions, that you can prove an interesting result. However, I don't know any Poincare-Lalonde formula for almost analytic extensions.
Or something?
No, the problem is I don't know. Everything would work fine except one thing, maybe two. First, I don't know a Poincare-Lelong formula. First, almost analytic extensions are really not unique, but we can probably find a fairly canonical one. But I can't construct a delta function on the zero set by just taking derivatives of the log modulus. Number one, in the smooth case. That's big hang-up, number one. Number two, we use the compactness of this family of plurisubharmonic functions. If we made almost analytic extensions of smooth functions, is there any such theorem? But mainly, we just don't have a delta function. We don't have a delta function. I mean, I think it's a great question. I would not be surprised if a sufficiently ingenious argument might find at least some cases where you could imitate this for C infinity metrics. But
I was attending the other workshop, homological things. It seems to they have a way, like the algebra way, to deal with delta functions.
Go here.
yeah, I don't know. I didn't go to that workshop. Maybe I would have learned how to do it.